Hi, my name is Kaan Sancak, and I'm a PhD student at Georgia Tech. Today, I'm going to present our work, MG-GCN, a scalable multi-GPU GCN training framework. In our efforts, we try to parallelize graph convolutional networks, which are a type of graph neural network. And this work is a collaboration with my lab mate, Muhammed Fatih Balin, and our advisor, Umit Catalyurek. We are all from Georgia Tech. So, to start with, recently machine learning has made a great progress, and deep learning has been the driving factor in the improvements in AI and machine learning. However, most of the trends in deep learning have been done in uh, computer vision and natural language processing related tasks, where the inputs have fixed structures. What I mean by that is, for example, for computer vision related tasks, the inputs are usually images, and images are represented by fixed size grids. And for NLP tasks, the inputs are usually texts, where the texts are represented by sequences. And this basically means that the modern machine learning toolbox is designed for simple sequences and grids. However, the real world data can be much more complex than that, and they don't have to live on the grids. They might require more irregular modeling, such as modeling with graphs. And in the recent years, graph neural networks have been gaining attention because of their ability to generalize deep neural network operations into graphs. And actually, in many of they seem to perform the state-of-the-art results in many of the problems where the problem can be modeled by a network of interaction. And by network of interaction, we mean that a graph of nodes where the nodes are connected by edges. And under this category falls everything from social networks to knowledge graphs to biological networks, molecular networks, protein networks, and road networks, and many other. And depending on what type of graph we have, graph neural networks might have different tasks. For example, in a social network, we can use graph neural networks for link prediction, which might be represented as a friend suggestion. And for images, we can use them for object classification and detection. For molecular or protein networks, we can use them for drug discovery. For example, for road networks, we can use them for combinatorial optimizations. And here is the quick overview of our talk. And I will start with the introduction and define our problem. Then I will go into some details of the mathematical computations in graph neural networks. Then I will explain our framework, MG-GCN, and explain our optimizations. Then I will present our experimental evaluation and conclude this talk. So yes, GNS performs well on graphs, but we need to store the graph somewhere. We need to store the vertex and edge features if there's any, and we also need to store the intermediate outputs that are required by different computations. So it turns out that training GNNs on large graphs require a lot of memory, and GPUs are fast, but they have very limited memory. Today, a GPU might have up to 80 gigabytes of memory, whereas a CPU based system might have 6 terabytes of memory. So the GPUs have very limited memories, and actually they are quite expensive. So it turns out that existing frameworks don't utilize the memory efficiently, and they actually allocate excessive buffers for intermediate outputs. So this is kind of a background, but just like in any traditional deep neural network training, there is two approaches to graph neural network training. The first one is called full batch training, where we use the full graph to train and we compute the exact loss function over the full dataset. On the other hand, the second approach is called mini batch training, where we do the training on a mini batch of samples using approximate loss and gradients. And this can be think of sampling nodes and then making the computation on the ego network of the sampled nodes. So we don't use the full graph, but we use a subgraph of the whole graph. So what are the problems with these two approaches? And for the full batch training, we use the full graph to train the model, but the memory requirement for large graphs can quickly exceed the memory capacity of a single accelerator. On the other hand, we resolve this problem in mini batch training by reducing the working set by creating a mini batch of vertex samples to train our model, but it turns out that if we have a deep enough graph neural network model, we can end up reaching the full graph anyway. And this happens because if we have a deep enough graph neural network model, the echo network of those nodes might reach the full graph. And this is also known as neighborhood explosion phenomenon. And in our work, we actually show that it is possible to do the full batch training with a better runtime than existing frameworks while consuming much more less memory. So to give you a little background, and so this is the high-level representation of the graph neural network. And here we have the input graph, and it might have some input features on its edges or vertices. Then we have the graph neural network layers. So in each layer, our graph goes into a transformation. But in each layer, we actually have the same exact graph, just with transformed features. And this transformation is defined by the specific layer itself. So we have the same graph with transformed features in each layer. And it is a general practice that between each layer, we have a nonlinear activation function. And if we stack up, depending on our architecture, if we stack up multiple layers, we can stack up multiple layers. And in each layer, our graph will go into these transformations. And eventually, we will get the output. And depending on our downstream tasks, we can have different classification tasks. For example, we might have a node level classification where we predict or we do a prediction for each individual vertex. Or we might have a graph classification problem where we have a single result for the full graph. And this is usually done by aggregating the results of individual vertices. Or we might have a link prediction task. And this is usually done by combining the source and destination embeddings of an edge. And here on the bottom we have the formulation for the full batch graph neural network training. Here we have the A, which is the sparse adjacency matrix. Then we have the H. H is the input feature matrix, and W, which is the matrix for layer weights. And basically, what happens is here we multiply the input feature matrix with layer weight matrices, and we get the transformed features in the output feature space. Then to aggregate the messages for all neighbors for each vertex, we multiply it with the sparse adjacency matrix. And to get the output for the next layer, we basically feed the result into a nonlinear activation function. So this can be seen as in the forward pass, we do a GAM operation between the input matrix and the trainable weight matrix. And then we do an SPMM between the intermediate result and the sparse adjacency matrix. And finally, we feed our result into a nonlinear activation function to compute the next layer's output. And in the backward pass, we actually do the exactly same thing, but in the reverse order. So we first do the activation function, then we do the SPMM, and then we do two GAM operations. One to compute the gradients of the layer weights, one to compute the gradients of the layer outputs. So this is the vertex level representation of our computations. So basically for each vertex, we aggregate the messages from the neighbors. And here, if we consider the red node, it aggregates messages from its neighbors. The messages are aggregated by the red arrows. And this can be seen on the right-hand side of this formulation. And on the left side, we see the blue formulation, which is marked by the blue arrow. And this is also called skip connection. And this basically helps a vertex to aggregate embeddings from its previous layer output. And then we feed the result into nonlinear activation function. And this is the forward pass. So in the backward pass, we basically do the same things, but in the reverse order. So basically, we reverse the edges. Now, let me talk about our framework, MG-GCN, which stands for Multi-GPU Graph Convolutional Network. One of the first things we have realized about existing frameworks was their usage of multiple buffers for different intermediate outputs. So while we are designing our system, we have tried to use minimum number of possible buffers. Here we see a representation of a L-layer GCN model with shared buffers across layers in our framework. And these three buffers, actually, they're allocated once per GPU and shared across the whole layers, meaning that they do not scale with the number of layers. The first two buffers, BC1 and BC2, they are broadcast buffers for communication between GPUs. And we need two of them to enable overlap, communication, and computation. The H1W on the other side, it's a temporary result buffer for between the SPMM and GEM operation. In our design, each GPU has a part of the graph, the input and the intermediate embeddings, and the GPUs communicate in each layer in order to exchange messages between their assigned vertices. And this is how we assign the vertices. In our framework, we do use 1D partitioning strategy in order to partition our matrices. In the case of the sparse adjacency matrix, we partition it by its rows, meaning that each GPU will hold a set of rows, vertices. And we also partition the sparse adjacency matrix by its columns, and each column partition is actually used in different stages of the SPMM. And what I mean by that is we do perform the SPMM operation in multiple stages, and this is how it works. In the first stage of the SPMM, the first GPU, which holds this blue section in the HW buffer, it broadcasts its local portion to all the other GPUs. Now that all the other GPUs have that portion, they can actually make a local SPMM with their adjacency matrix portions and aggregate the results. And this is actually the only communication needed in our framework, and we do not require any additional communication. And then this process is repeated for the second GPU with the purple part and repeated until the last GPU broadcasts its local portion and the last aggregation is done. So we have as many stages as the number of GPUs. And another thing to note is that we actually hide this communication by overlapping it with computation. So let me go into the little bit more details on the memory optimizations we made. In our framework, there are two types of buffers. The first type is the ones that are shared across layers, and we have already mentioned these before. They do not scale with the number of layers, and they are also shared between the forward and the backward pass of the same layer. And we also have a second type of buffer that is private to a layer. And these buffers, we allocate them once per layer per GPU, but they are still shared between the forward and the backward passes of the same layer. And we do need this AHW buffer, which is private to a layer, because we want to avoid the recompetition during the backward phase of a layer. This is how overlapping computation and communication works in our framework. So NVIDIA GPUs, they work with stream abstractions, and the computation on a stream is serialized. Then we can actually have two separate streams for computation and communication, and we can create dependencies between the two by deciding on which communication is needed by which computation. Here, we see our results on a 4 GPU setting. In our figure, the yellow bars, they represent the communication times, and the blue bars represents the computation times. And the numbers on the bars, they indicate the stage of the SPMM operation. So we have 4 GPUs and 4 stages. We see that if there is no overlap of computation and communication, all of the operations are serialized, meaning that there is first communication, then computation, computation, and so on. However, if we enable communication and computation overlap, we see that after the first communication, all of the communications are hidden by computations. And this helps us to greatly save time on the SPMM operations. We have also performed other optimizations. For example, we changed the order of the SPMM and GEM operations for less costly SPMM operation, depending on the feature dimensions of the previous and the next layers. And During the first layer backward propagation, let's say that if we did the SPMM first in the forward pass, which means that SPMM will be the last operation in the backward, then it turns out that we actually don't need to do SPMM at all, because the input features of the first layer, they do not require gradients. However, if we did the GAM first, meaning that the GAM will be the last operation, then we actually need to perform the SPMM operation. However, actually, we show that instead of SPMM, we can do an element-wise scaling with diagonal matrix, which is, in our case, is the identity matrix. We also randomly permute our adjacency matrix to have a better load balance on the edges. Now, let's talk about experimental evaluation. Here, we have our experimental setup as well as our datasets. In our experiments, we have used 6 different datasets, and they are as small as Cora, which has 3.3K vertices and 9.2K edges, and they are as big as Papers, which has 111 million vertices and 1.61 billion edges. In our experiments, we have used 2 different servers. The first one is DGX1 server with 8 NVIDIA V100 GPUs, and the second one is DGX A100 with 8 NVIDIA A100 GPUs. And in our experiments, we have mostly used GCN model with 2 layers that had 512 byte hidden layer. And in some of our experiments, we have also used the GCN model with 3 layers that had 256 byte hidden layer. Note that even though some of the datasets here are the largest available graph neural network benchmark datasets, we are able to fit them into a single machine with 8 GPUs. So before going into the details, we wanted to understand the operations that are involved in graph neural network computations. And to do that, we tried to get the runtime decomposition of the involved kernels. And these are the 5 kernels that we found that quite important: the activation function, the ADOM optimizer, GAM, loss layer computation, and SPMM. And when we look at the larger graphs we have, we see that actually the most of the time is spent on the SPMM, and the others are the others runtimes is insignificant compared to the SPMM runtime. So that's why in our work, we try to focus on this part and parallelize and redistribute the workload on this part. So here we present our results on permitting the adjacency matrix and also applying communication computation overlap. And we try to show our optimizations gradually, meaning that we first apply permutation and then we apply overlapping communication computation on top of that. And all of the numbers here are normalized with respect to non-optimized versions for a given number of GPUs. And in this figure, we see that as we increase the number of GPUs, actually the permutation effect becomes more significant. And this is expected because as we increase the number of GPUs, we may run into load balancing issues. And that's why we have been applying the permutation at the beginning. And we also see that on top of permutation, if we apply overlapping communication computation, we can get up to 60% performance increase compared to the baseline. So we have done another experiment to understand the impact of average degree on the speed up we can get on GCN operations. And here what we did is basically we took one of the smaller datasets we have, which is ArchiveX in this case, and we kept the distribution and the structure the same, but we increased the number of edges, meaning that we increased the average degree. So we have scaled ArchiveX graph from 1x, which is the ArchiveX graph itself, and we scaled up to 128x. And when we look at the figure, we see that as we increase the average degree, our speed up also scales. And this is expected because the only operation that is affected by the average degree in GCN computation is SPMM. and all of the other operations remain the same. And the longer the SBMM operation, the better we can hide the communication. So we get a higher speed up by increasing it. In these figures, we compare MG-GCN with two different baselines. The first baseline is DGL, and DGL is a popular framework for computing graph neural network operations. And we use DGL with its full-batch training options on a single GPU. And we also compare with JAGNet, which is a full-batch multi-GPU GNN training framework. And on the right side, we show our speed-up results with respect to DGL's 1 GPU full-batch training option. And we see that on a single GPU, our framework is 3 times faster than DGL single GPU result. And when we use multiple GPUs, our framework is 15 times faster. However, we see that the other multi-GPU framework, Cognet, is only 5 times faster than DGL 1 GPU result. Here we run another experiment to understand the memory consumptions of different frameworks. Basically, in these figures, we show on the x-axis, we show a memory budget per GPU in gigabytes. And on the y-axis, we show the number of layers. Basically, what this figure means is that given a memory budget per GPU, how many layers can I fit into my model? And we see that on a single GPU, MG-GCN can fit twice as many as layers than GGL. And on the multi-GPU case, MG-GCN can fit 3 times more than JAGNet, 3 times more layers than JAGNet. To conclude our presentation, we show that MG-GCN with its memory optimizations enables full-batch training on the largest available GNN datasets on a single node. And we don't mention this in the presentation, but we show it in the paper, that actually MG-GCN is faster than the distributed CPU-based system DisGNN by 10x while consuming the 10x less energy. And we also show that MG-GCN uses 2x less memory per layer than the popular DGL framework on a single GPU and 3x less memory per layer than JAGNet in the multi-GPU case. Thanks for listening to our talk, and you can reach me out from my mail address or you can visit our lab page. Thank you.